I will just wait a moment while everyone's still joining in. Can everybody hear me okay? Okay, good. I hope you are all having a great day, and I hope you're excited to join me on this calculus class today. Okay, so as you remember, we are still discussing integrals, and that will be the subject for today's class. Okay. I am trying to keep my voice down a little bit as I feel like I am becoming sick, so I hope you don't mind. Okay. So I can tell most of you have joined by now, so let's get started. Okay, so I have not written a title right here, but if you want, it is just integrals, so let me do that right now. Please excuse me for my awful handwriting. So that is the title for today's class, integrals. Okay. So let me read to you the first chapter. In mathematics, an integral assigns numbers to functions in a way that can describe displacement, area, volume, and other concepts that arise by combining infinitesimal data. Integration is one of the two main operations of calculus, with its inverse operation, differentiation, being the other. Given a function f of a real variable x and an interval a to b of the real line, the definite integral is pictured here. You're welcome to copy this into your notebooks if you're taking notes. So, what we have here is the function f, the variable x, and a closed interval from a to b. Okay. This can be interpreted informally as the side area of the region in the xy plane that is bounded by the graph of x, the x-axis, and the vertical lines x equals a and x equals b. So let me draw a picture of that. So here we have the y-axis. So y, x-axis, and let's say that our graph goes just like that. Okay. So it is bounded by the graph of f, the x-axis, and vertical lines x equals a and x equals b, just like so. The area above the x-axis adds to the total, and that below the x-axis subtracts from the total. The operation of integration up to an additive constant is the inverse of the operation of differentiation. For this reason, the term integral may also refer to the related notion of the antiderivative, a function f, whose derivative is the given function f. In this case, it is called an indefinite integral and is written like so. Okay, so here we have the function f, and it's two ways to mark the integral of the function f right here. So these two are the same thing, okay? So an easy way to remember is if we have the integral, and then we have the derivative. These two are synced up. So this is the f, and there we have f. Okay. So here with the integral, the f is capitalized, and here it is not, to differentiate between the two. Okay? Is everyone still following? Does anyone have any questions? Okay, let's continue. So, the integrals discussed in this article are those termed definite integrals, it is the fundamental theorem of calculus that connects differentiation with the definite integral. If f is a continuous real-valued function defined on a closed interval a to b, and we can see the symbols for the closed interval right there, then once an antiderivative f of f is known, the definite integral of f over that interval is given by and here we have that. I will take a pause right now so you can copy this into your notebooks. Okay, now let me draw a picture of this once again. So here we have the y-axis and the x-axis, and let's say that our function f goes just like that. Now, to determine the integral between a and b, which is right here, we will first integrate the function f and then subtract. So here we have b, so this is right here and right there, and that will give us the integral right here. Okay. Okay, is everyone still following? Yes, I hope you are not on your phones during this lesson, since this will be, integration is a big part of the test that's coming up. Okay, so you need to stay focused, alright? So here we have a little bit of history of integration, which I know may not seem that interesting to all of you, but I find it important to go through all of this. Okay, so the principles of integration were formulated independently by Isaac Newton and Gottfried Wilhelm Leibniz in the late 17th century, who thought of the integral as an infinite sum of rectangles of infinitesimal width. Bernard Riemann gave a rigorous mathematical definition of integrals. It is based on a limiting procedure that approximates the area of a curvilinear region by breaking the region into thin vertical slabs. Okay, does everyone understand what this means? So, even though it was done in the 17th century, it is still the way that we think of an integral. So, thin vertical slabs mean if I have this integral right here, I would do like so, and this would be all square. So okay, let me show you a little bit better. So if the graph went like so, and here are the lines, they would just go like so. So it is not completely accurate, since we still have this space lacking right here. But like Isaac Newton I lost thoughts. He thought of the integral as an infinite sum of rectangles of infinitesimal width. So right now, let's say the width is c, so all of these are c and c, c. But when we get more of these rectangles, so let's get a few more in there and so on, and I hope you get the idea. So that eventually all of these small slabs have the width which is infinitely small. Okay, well, it's not minus, sorry. So infinitely small, and then we're approaching the actual integral. So we have a picture right here. So let's continue, okay? Beginning in the 19th century, more sophisticated notions of integrals began to appear, where the type of function, as well as the domain over which the integration is performed has been generalized. A line integral is defined for functions of two or more variables, and the interval of integration from A to B is replaced by a curve connecting the two endpoints. In a surface integral, the curve is replaced by a piece of a surface in three-dimensional space. Okay. So next we have a bit more practical. So replacing the A and the B that we had right here and right here with 0 and 1. And our function is the square root of x. So what is the area under the function f in the interval from 0 to 1? Okay. So here we have the first approximation. Let's look at the unit square given by the sides x equals 0, which we have right here, to x equals 1. So right here, or actually right here. And then the function value right here is 0, and right here it's 1. So, like it states it here, the area is exactly 1. Okay, but if we look at this graph, we can clearly tell that the true value of the integral is less than 1. Okay, so then we can start to approximate by decreasing the width of the approximation rectangles. So right here, so the smaller these rectangles are, the more we're approaching the actual integral, the actual side of this part right here. Okay? If you want to draw this graph right here, I will just wait a moment. Okay? If you have any questions, feel free to put your microphone on and I can answer them. But otherwise, try and keep your microphone turned off so that we don't get any distractions during this class. Okay. Alright, let's continue. So, as we start summing these areas or these small rectangles that we just saw, the approximation starts getting better. Okay? We are taking a sum of finitely many function values of f multiplied with the differences of two subsequent approximation points. We can easily see that the approximation is still too large. So just bringing back this image right here. So if we round this to 0.75, we can tell that this area is still smaller than that. Okay? So, using more steps produces a closer approximation, but will always be too high and will never be exact. Alternatively, replacing these subintervals by ones with the left and height of each piece, we will get an approximation that is too low. For example, with 12 such subintervals, we will get an approximate value of the area of 0.6203. The key idea is the transition from adding finitely many differences of the approximation points multiplied by their respective function values to using infinitely many fine infinitesimal steps, when the transition is completed in the above example, it turns out that the area under the curve within the stated bounds is 2/3. Okay? Let's move on to numerical integration. Here we have some general information on the subject. Feel free to take a screenshot of the screen right now if you want to go through this. But for today, we will move on. Okay. Okay. So here we have, I'm sorry that the picture is a bit low quality, but we have an integral or an integration range that is divided into 16 equal pieces and computes function values. Okay, so let me try and maybe okay, well, I will send this image to you after class so that you can see it a little bit better. But basically, I hope you can all tell that right here is the value x and then the function value right there. Okay, and like said, there is 16 equal pieces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. So we have 16 values, but since our integration points right here, so let's say there are 16, approximately, we have 16 pieces, but the function value or the points in which we count the variable, there are 17, since we have to take into consideration these ones, so the last one and the first one. Okay, so using the left end of each piece, the rectangle method sums 16 function values and multiplies by step with h, here 0.25, so one of these would be 0.25. Okay, and you can repeat this as many times as needed to get approximation that is suitable for the calculation that you're doing. Okay? But a better approach replaces the rectangles used in a Riemann sum with trapezoids. The trapezoid rule is almost as easy to calculate, since it sums all 17 function values but weighs the first and last one by half. Okay? So here we have 0.25, that is right here, and it is applied to all of these. Okay? But with the Riemann sum that uses trapezoids, we weigh the first and the last one by half. Okay? And again multiplies by the step with. This immediately proves the approximation to 3.76925, which is noticeably more accurate. Okay, the idea behind the trapezoid rule that more accurate approximations to the function yield better approximations to the integral, and that can be carried further. Okay. So Riemann sums, the trapezoid rule, and Simpson's rule are examples of a family of quadrature rules called Newton Cotes formulas. Here we have different techniques of integration. We will skip this part, however, I would like to point out that here we also discuss the antiderivative, so the inverse. So if we have the function f, its antiderivative like so. Okay. It is often convenient to algebraically manipulate the integrand such that other integration techniques, such as integration by substitution, may be used. To calculate the n times repeated antiderivative of a function f, Cauchy's formula is useful. We have it right here. Feel free to take a screenshot once again. You're also free to Google this, since unfortunately the quality is a bit low. Okay, but I will again take a moment to give you a moment to copy this into your notebooks if you'd like. I do hope that you have been making notes during this class. Okay. Okay. So as you can tell, this is the last page of the notes. I hope you are all still here, and I hope you enjoyed this class. We will see again in the next class. I have sent you the course schedule. It is in all of your emails. Sorry, for a moment I thought I had forgot to send it, but I think I did. So there you can find the course schedule, and I will always send you a link to these Zoom classes. We'll be doing these moving from integration to a bit more difficult calculus exercises, okay? So I hope you take the time to go through these notes or your own notes after the class, just so that the techniques of integration are really that you remember them, okay? Since we do have a test coming up, like I said earlier, I hope no one has forgotten about that. Okay, well, I will end the meeting now. We will see during the next class. Okay.